Hi, my name is Christopher and I am Business Manager here at the Danish Technological Institute. This course I will talk about Fused Deposition Modeling, also known as FDM 3D printing. When we take a look at the chart for the different additive manufacturing technologies, we can see that we are looking into material extrusion, where the specific technology is Fused Deposition Modeling, also called FDM, where we have the ability to print in different materials, example composite, plastics and metals. If we look at the ISO standard, the material commonly used is polymer. The fusion state is a thermal reaction bonding, where the material comes in the form of filament. Then we use a deposition nozzle to distribute the filament. The basic AM principle is called extrusion of melted material, and the process category is material extrusion. So first up, we will take a look at what is Fused Deposition Modeling. Fused Deposition Modeling, FDM, also known as FFF, Fused Filament Fabrication, it depends on who you ask, is built up by 4 components. We have the build platform, where the part is built on. Then we have the extruder that moves around and deposits the material. Then we have the filament that is coming out of the nozzle or the extruder. And then we have this XYZ configuration that in some way moves the extruder around the build platform. The process flow for FDM printing is that first the extruder and the build platform is heated up, and then the print can start. Then the extruder distributes the filament on the platform, and then either the platform lowers or the extruder rises up between each layer. Then the next layer is distributed, and this cycle will continue until the print is finished. And when the part is finished, you can remove it from the platform almost immediately. When we look at FDM printing, there is mainly 4 different machine configurations that is used to move the nozzle or the build platform around when printing. We have the Cartesian, the polar, the delta and the robotic arm. In the upper left corner we see an example of a Cartesian FDM printer. Here we have an extruder that moves in the XY plane, and then the platform will lower down in the Z plane. In the Cartesian setup we have a static XY table, as you might know it from a 3-axis milling machine, but it's instead of milling, here we just extrude material. In the upper right corner we see the delta printer. Here we have 3 linear actuators that moves the print head around and up and down in the X, Y and Z direction, and the nozzle then deposits the material on a static build platform. In the lower left corner we have the polar 3D printer. Here the print platform is rotating around itself and moving forward and backwards in the Y direction, and the nozzle is only moving up and down in the Z direction. In the lower right corner we have the robotic arm. On the robotic arm FDM printer we have again a static build platform, and then the robotic arm do all the motion. A robotic arm, as you might know, can move in all directions, and the difference here is only that we have fitted a extruder to the end instead of a gripper or something else. The robotic arm might be the most complex of these types of printers, but it's also the one with the most degrees of freedom, where you don't have a defined space that it can print within. Of these 4 types of FDM printers, the Cartesian model is probably the most commonly used today. Usually when people think of FDM printers, they imagine something like the machine on the left, which is a cheap desktop printer. But it's important to mention that FDM printers come in various different sizes and prices, like the one we see on the right, that is an industrial printer that can print much bigger and much faster. Now it's time to have a look at the pros and cons of the FDM technology. The main advantage of FDM printing is that it's fast and it's cheap. It is a very fast way of making prototypes, and the machines can be used to make cost-efficient parts at low volume. Also, the materials and the machines are generally very low cost, and it's easy and fast to switch between different materials. One of the disadvantages of using FDM printing is that you need support structure. You need support structure when you have a part with an overhang that is less than 45 degrees. And this support structure has to be removed after printing to have the final finished part. It is possible to make the support removal easier by having a dual extrusion setup where you print the support material in a dissolvable material. You can see an example of this in the picture to the right. Another disadvantage of FDM printing is that you will get a rather rough surface. When you print, you will have these visible layers as you see on the picture to the right. And if you want to remove them and get a nice and smooth surface, it will require some post-processing. Both a disadvantage and advantage of FDM printing is the post-process. You have to remove the support structure, which takes time, but you also have the opportunity to have a nicer surface finish of the part, create connections between different parts by cold welding them together, and get a better aesthetics by polishing or coating or vapor smoothing the parts. Another benefit of FDM printing is that you can have many different mechanical properties. The mechanical properties follows the thermoplastic which is used, and there is so many different plastics to choose from when using FDM printing. One thing to be aware of is that the orientation of the part you're printing has an effect on the strength. For instance, the tensile strength can be up to 4 to 5 times lower in the Z direction than the XY direction. Another advantage of FDM printing is the new developments that is going on. For instance, if you want to improve the material properties, you can do this by CFF or metal FDM printing. CFF is the continuous filament fabrication, where you use a continuous string of either carbon fiber, fiberglass or Kevlar to put into the part that you're printing. You can also use metal FDM, where you print with filament that has metal powder in it. When you print in this way, you have this green part after printing, then you have to wash the part and then center it in an oven. Afterwards, then you will have a finished metal part. If we look at the use cases for FDM printing, it is fast for prototyping and usually slow for production. As an example, here we have a charging port for electric vehicles, where FDM printing was used for fast prototyping, and later they switched to another type of printing for production. If we look closer at prototyping versus production, in this example, this part will take around 10 hours for printing one part. If you instead want to print 6 parts at full build plate, it will take around 50 hours. This is almost a linear increase in time when you increase the number of parts. This confirms that FDM printing is great for rapid prototyping, but quite slow for medium to large batch production. In comparison, for this part, an SLS printer will be around 15 times faster in batch production than using an FDM printer. If we look at the printing process and the time it takes for the different stages, we can see that heating up the extruder and the build platform only takes 5 minutes or so, and then the printing time is the one that is linear due to the number of parts we are printing, where a layer takes from 1 to 10 minutes for each layer, depending on how many parts you fit into a platform. And at the end, we have to remove the parts, which is done very fast. So to sum up the pros and cons for FDM printing, on the pro side, we have a cheap 3D printer that is great for prototypes, and it has a wide range of materials to choose from. It is great for beginners, and if you want even stronger parts, you can use CFF or metal FDM printing. Among the downsides, we have the need for support structure, and we have the anisotropic properties. Also, the layer structures are visible after printing, and it requires some post-processing if you want nice surfaces. And finally, it's not suited for high volume production due to the slow printing time. Now it's time to look at the different design possibilities for FDM printing. When you print using FDM printing, you use infills or lattice structures. Infills are the material inside the boundary of the part. If you have an infill of 100%, then the part is completely solid. And if you have an infill of 20%, then you will have these hollow cavities within the part. Having a less dense part will save you weight and money and material and print time. But you should be aware when using infill, you will change the mechanical properties of the part. And if you have a low infill, you will also have a weaker part. Another design possibility with FDM printing is the ability to print big parts. This is because it's only the XYZ configuration that limits the size of the parts you print. As an example, the University of Maine has here printed a fully functional boat in one piece. As mentioned earlier, it is possible to make reinforced parts with continuous filament fabrication. In this case, we have a lifting tool that is used to lift metal cylinders. On the picture in the upper right corner, we see the original tool that is milled out from solid steel. Below we have the 3D printed part, which is reinforced with carbon fiber. This part is 75% lighter and it costs around €1,000 less per tool. Next up, we are going to look at the design guidelines for FDM printing. Here we have some design rules for FDM 3D printing provided by Hobbs. Here we can see all the things you have to take into consideration when designing for FDM printing. I would like to take a look at the horizontal bridges, the holes and the tolerances. A horizontal bridge is the span a technology can print between 2 points without support structure. For FDM printing, a bridge should not be any longer than 10 millimeters. With long unsupported horizontal spans, you risk having poor bridging. High print speed will make bridging even worse, as you can see in the picture up here in the right corner. If you dial down the print speed, you can make decent bridges spanning further than 10 millimeters. To avoid poor bridging, you want to align the parts or use support structure when needed. Next up is holes. The minimum recommended diameter of a hole should be around 2 millimeters. And you should be aware that it can be troublesome to print holes in the XY plane. This is because you'll need support material inside the hole. Therefore, you need to orient the part conveniently to avoid this support structure. Holes should be drilled out after printing if you need some very precise tolerances. And usually you should just completely avoid having horizontal holes. The reason why the diameter of the hole shouldn't be smaller than 2 millimeters is because the filament is compressed while printing. So the nozzle, while squeezing out the filament, will make it a little oval, meaning that the actual diameter will decrease compared to the 3D model. FDM printing has a general tolerance of plus minus 0.5% with a lower limit of 0.5 millimeters. This is because when the part is cooling down, the plastics has the risk of shrinking and warping. Shrinking can be hard to predict, but it gets worse with higher print temperatures. To the right, you see an example of how a part can warp while it's cooling down. To prevent this from happening, you could use more support material or even glue to stick the part to the build plate. Now it's time to look at some of the many different materials for FDM printing. This pyramid shows some of the basic materials for FDM printing, where in the bottom we have the commodity materials going through the engineering materials all the way to high performance. And the further we go up the pyramid, the higher the temperature is needed to print it and the more it costs, but you also get a better performance out of the materials. Two of the popular commodity materials are PLA and ABS plastics, where the PLA is made from biodegradable material, and the ABS plastic is made from fossil fuels but can be recycled multiple times. Some of the reasons you should choose PLA is because it's easy to print with due to the low printing temperature. Printing with PLA, you don't need a heated print bed and therefore can use a cheaper printer printing this material. It's easy to post-process, it has a fairly good heat resistance, and then we have the low environmental impact. You can also choose ABS plastics. It has great stiffness and durability, it can be recycled multiple times, it is great for machining, and it has a higher temperature resistance. In addition to standard filaments, you can get filaments with additives. This could be carbon fiber filaments, magnetically detectable filaments, aluminium reinforced or glass reinforced filaments. All the materials listed here are commercially available. Now it's time to look at what you can actually print with FDM printing. When using a standard desktop FDM printer, it is possible to print rapid prototypes and spare parts that is good enough, and all sorts of custom tools and gadgets. Also, there are many online communities where you can go and find a design you like and print it right away for free. Looking at a specific case, we here have a container lid gripper from the company NewTek. NewTek is printing the parts themselves using FDM printing, making the parts cheap, and they have the design freedom, and they have the possibility to change the design. The only post-processing needed is support removal, and they print around 40 to 80 parts per year. Here you can see the machine that NewTek has built, where they use the lid gripper to grab the lid and turn it around and place it on top of the container. Here I have made this graph explaining the economy of using 3D printing versus conventional manufacturing. Up here we can see some advantages, and down here we have the disadvantages. For this part we can see that in the development phase we have the design freedom and fast design iterations as some advantages. In the production phase, another benefit is that there is no expensive tooling needed to produce the parts. The price per part will be a little higher than if you had an injection molding tool, but here you don't have to invest in the tool as just mentioned. The final benefit of the part is in the application phase, where you don't need an inventory of spare parts. You simply just print it on demand when you need it. Here we have the last case where Airbus is using FDM printing to save weight and money on printing their space panels. As you can see in the picture, there is a very complex geometry with lattice structures that helps to reduce weight. And by using FDM printing, this part is actually 15% lighter than the original. So let's look at the economy of 3D printing versus conventional manufacturing. Here we see that in the development of the part, we can make this lightweight, complex design, and we can do it very fast. The advantage in the production phase is that we have fewer parts to certify and assemble because we have consolidated multiple parts into one. The parts are more expensive to produce, but the 15% decrease in weight equals to a lower fuel consumption and thereby a better fuel economy. Let's take a look at the health, safety and environment. For FDM printing, there are two general hazards: mechanical hazards and emission of particles. For mechanical hazards, we have hot extruders, nozzles and motors. These extruders will move around and they can be between 190 to 300 degrees Celsius. In some cases, the nozzle can even be up to 480 degrees Celsius. So there is both the risk of you getting burned and the printer igniting itself or its surroundings. The second hazard is the emission of small particles down to 0.1 microns, depending on the filament. So this is an inhalation risk. Looking at the filament inhalation risk, we have nylon and ABS that can be very harmful. The high levels of styrene can cause headaches and drowsiness and fatigue, but there are several ways you can mitigate these emissions of particles. you have to make sure to choose the right material for the part you're printing. Make sure to use an exhaust fan, a filter, or to ventilate, open a window or something like that. Also, you should limit the time you spend close to the printer, and it is recommended to use an enclosure while printing. We looked at 3D printing itself in a previous chapter, so now we will have a look at the 3D printing preparation process. So the first thing you have to do is to get the 3D model that you want to print. You can go ahead and design it yourself in some kind of CAD software. You can also take an existing part and scan it, either with a scanner or your mobile phone. And finally, you can go and acquire a model on one of the many online services out there. Next up is the print orientation. We have to choose the right orientation of the part to save support material. Furthermore, a good orientation will give you a better aesthetics and quality of the part. Also, the orientation can have a significant impact on the build time. If we look at the example here, the horizontal part has around 100 layers and the vertical part has 300 layers, meaning that it will take 3 times as long to print. You also have to be aware that the orientation will affect the mechanical properties of the parts, because a part will be stronger in the XY direction than in the Z direction. Then we have to add some support material. The support material depends on the model geometry and the orientation of the model. Usually the slicer will give you an example of how the support material could look, as we can see down here in the picture, where we see 3 different types of support structure. But you have to be aware that more support material adds time and cost to the print. Before the 3D model is ready to print, it has to be translated into machine instruction. This is done by slicing it into thin layers and converting that into G-code, which the machine can understand. This is done with a slicing software, and there is different softwares for different kinds of printers. Now we have to prepare the printer itself by adding spools of filament, and here it's important that you choose the right filament for the application you're going to print, but also the same filament as you used in the slicer software. Then you have to take the filament and put it into the extruder and make sure that it is all the way through before starting to print. Finally, you need to be aware that there are different properties for different filaments. The final step before printing is bed leveling. You have to have a level print bed to be able to print good first layers. As you can see an example over here, if the nozzle is too far from the bed, you get this stringy mess, and if the nozzle is too close to the platform, you get this squeezed out, and it's just perfect when it looks something like this over here. So generally it's impossible to get a perfect print if your bed is not level in the first place. Below you can see some of the problems that can be caused by bad bed leveling. For example, you can have under extrusion, where it seems that the nozzle is clogged and not enough filament gets out because you're too close to the build platform. Also, you can have poor adhesion if you're too far away from the build platform, and if you're way too close, you can physically damage your print or the print bed itself. During the past years, bed leveling has become a little bit easier because the printers themselves has incorporated magnets and sensors in the build plate, so it's able to level itself. When the printing is done, we have to post-process the parts, and that's what we are going to take a look at now. Here we have an overview of the different post-processes. We have the mandatory, the surface finish, the connecting, and the aesthetics. I will cover these individually in the next couple of slides. First, we have the mandatory post-processing, which is removing the support structures. And there are several different ways this can be done. It can be done manually with pliers, as you can see in the picture here. You can also use dissolvable support structure, which dissolves in water or some kind of acid. If the support structure is removed in an incorrect way, you can damage the part and affect the physical properties of the part itself. If the model requires support material, it also often needs surface finish afterwards. To improve the surface finish, you have different options. For example, you can use sanding, media blasting or deburring. On the left you can see an example of using sandpaper, where a 600 grit sandpaper has been used to make the surface smoother. You can also media blast. Here is an example of glass blasting the part. And finally you have deburring, where you use ceramic chips to smoothen the surface. You should be aware that extensive post-processing can affect the tolerances of the part. If you want to connect two parts together, you can use what we call cold welding. This is done by applying acetone to the surfaces you want to combine with each other. Then the acetone will dissolve the part a little bit and you can stick the parts together. After welding the parts together, you can sand away the joints to make a nicer visual appearance. To improve the aesthetics of the part, you can choose to polish it by hand, and also you can prime the parts and afterwards paint it the colors that you want. Also, metal plating is an option, where you add a thin metal layer to the plastic part. And in the end we have vapor smoothing that will give the part this glossy surface from the acetone vapors that's in this chamber. If you wish to reuse your filament, it is possible to get a machine something like this, where you can take all your support structures and your failed print and put into a shredder and then extrude new filament from the old one. Just make sure that you don't mix materials in this process. Now we will look at quality assurance for FDM. For FDM printing, there's no specific quality control standards, and often extensive quality control is actually not needed because it's only used for prototyping. If, however, you need to do testing, you can do this by printing test specimens in accordance to international standards. You can also use CT scanning of the part to check dimensions and look for internal defects. To give an example of how quality control could look for FDM printing, here you can see the quality control process from Stratasys, where they have 4 main areas where they check the quality. First, you have to make sure that the part is printable and the dimensions is as the customer wants. Then they have the visual inspections. Then they do a physical measurements of the parts, and then they do a checkup when they ship the parts. Finally, we have some links and references if you want to learn more. First, we have some links for more general knowledge about additive manufacturing. And here we have some links specifically for FDM printing. That brings us to the end. Thank you for watching.